So, what we're talking about today, as I said, is the introduction to Chapter 7, which is on internal convection. So what we're going to do is a quick recap. Let me zoom in. What's with this? Quick recap of the materials from Chapter 7. We're going to discuss velocity and thermal fully developed flows. And we're going to discuss briefly the energy balance in a pipe. So, a quick recap here. All right, Chapter 7 was all about one variable. Okay, the whole thing was focused on finding one little letter, and that is H. So everything that dealt with convection and external flows came down to dealing with H in some form. That was either H bar or Hx, where H bar, right, we called the mean, and Hx we referred to as the local heat transfer coefficients. In general, we said that, right, H bar was usually the one that we chose to focus on, and we defined this as negative case of F, partial derivative of temperature with respect to Y, evaluated at Y equals 0, all over Ts minus T infinity. Let me prove that. There we go. Or, if you happen to know the mean Nusselt number, you could define it instead as H bar equals that mean Nusselt number times Kf over the length over which that mean is occurring. Okay, so if you're interested, I've used this example before, if you're interested in the mean heat transfer coefficient from this table, L is going to be the length of this table, and the Nusselt number is going to therefore refer to the mean over that entire length. How did we solve problems, right? There were two main ways. The first that came from Chapter 6. First of our solution methods dealt with exact solutions. All right, exact solutions. In general, work only when we have one of a very small subset of very simple problems. So, possible only for a small number of problems. And so the more practical approach took advantage of these things we called correlations. Much more practical. Very easy to practical. Much easier to apply, but requires pre-existing empirical or simulation data from which to infer these correlations. So things like turbulent flow over flat plates, flow around circular tubes. Okay, we don't have the ability to analyze those exactly using the theoretical tools at hand. So we have to hope that whatever situation we're looking at, there exists some experiment beforehand or some simulation that someone has carried out beforehand with the same dimensionless parameters. And if that's the case, then we can use those pre-existing correlations to pull out a Nusselt number. From that Nusselt number, we can get H, and from H, we can apply Newton's law of cooling to find our net rate of heat transfer. Okay. So that workflow, just again, works on the basis of finding dimensionless parameters, which we plug into our correlations to find Nusselt number, whether that's a mean or a local Nusselt number, and we use that to find H or Hx respectively, and use that to find Q or Q double prime. Okay, so that, right, is the general kind of arc that we followed for everything that is an external flow. But what is an external flow, and what makes that differ from what we're focusing on now, internal flows? Right. External flows, as the name implies, generally means the flow around the outside of something. So it usually means we're looking at some surface that is bounded by a flow that goes to infinity as you move away from the surface. It extends forever and ever and ever. And the big important thing about this is that when you have an unbounded flow, that means that these things that we refer to as boundary layers, right? Velocity boundary layers, thermal boundary layers, and species boundary layers, or concentration boundary layers, they can continue to grow infinitely. There's nothing that's going to get in the way of the flow and the evolution of these boundary layers. So they never reach this thing that we call a fully developed state. Internal flows, on the other hand, let's go ahead and write this down, right? Internal flows are defined by or share the feature of confinement. Right. So flow between multiple surfaces, as in flows through pipes and tubes, flow between plates, and flow through nozzles, or other type of orifices. So we're going to be spending the next 2 or 3 lectures discussing internal flows and focusing on 2 aspects. Right? The first is going to be the fluid dynamic aspect, and the thermal aspect, because both must be considered simultaneously in order to fully assess either one of them. All right. So what we're not doing is considering this idea of concentration. We discussed it in the last chapter. We said, look, it obeys the same math as we see for heat transfer. You can have mass convection, but that's not really the focus of our class, and we're not going to do much with it. So we're entirely kicking that to the curb for internal flows and focusing on the velocity and the thermal energy, okay, or momentum and thermal energy. Okay. So what we're going to do is spend today focusing on the flow through a circular pipe. This is a scenario that's familiar to us from fluids, but it bears revisiting. So, flow through a circular pipe. So if we have, right, a flow that is entering this pipe from an unconfined state. Okay, so if we have this is our pipe entrance at the left. Let's go ahead and draw that in as a nice filleted round entrance. Then, right, as soon as this thing enters, what's going to happen on the walls here? What condition is going to apply everywhere it's touching this? A non-slip condition, which means that we're going to end up with the growth of a boundary layer, right? So go ahead and refer to both of these as, right, this is a velocity boundary layer, and this is the same thing. So we've got these two boundary layers, or really one boundary layer that is extending around the entire perimeter of this pipe. Okay, you can think of this, a slice through this as looking like a donut. So this is an axial slice through the pipe that has a coordinate system of x looking downstream, and then this is our radial coordinate. So rather, it's a cylindrical coordinate system, I should say. So these boundary layers are going to grow, and if this were an external flow, right, this boundary layer would grow and grow and grow and grow infinitely. It would never stop. There's no asymptotic limit to the thickness of the boundary layer. But because it's an internal flow and there's this confinement, these two boundary layers are going to grow, and eventually at some point they're going to meet. And so when they meet, what happens is, of course, they have to stop growing. So upstream, right, we end up with this region of changing velocity in the boundary layer and constant velocity between them, right? But as soon as it reaches this point where they meet, our velocity remains constant at every point downstream, or our velocity distribution remains unchanged at every point downstream. So we refer to this point before they meet as developing flow. Okay. And we refer to every point downstream of that as fully developed flow. The other name we give to this region of developing flow is the hydrodynamic entrance region. And we define the point at which this fully developed flow occurs as, we'll go ahead and use the book's nomenclature here. This is X, FD, comma, H for the fully developed flow in a hydrodynamic sense. Okay. So the summary points here are boundary layers, right? Velocity type. Grow on all surfaces until meeting in the center. And then in the fully developed region, following condition holds, that dx of u, which is ordinarily, right, a function of the position in the pipe, both radially and axially, that variation with x goes to 0, which means that u becomes a function of r only, which is why the velocity distribution here and here can be identical. So the math, right, the theory behind fully developed flow, laminar, turbulent, etc., we've seen this all in fluids, and so we're going to sort of fast forward through this and just summarize a few of the key points and move on to the thermal considerations. If we need to come back and revisit any of this, we'll do that as we decide is necessary. So the important things about fully developed flow, we have this thing called a mean velocity, right? The mean velocity is basically the flow or the mass flow rate, m dot, divided by rho times the cross-sectional area mean velocity. The way we'd actually calculate this is um 1 over cross-sectional area, integral over the cross-sectional area of u dA, which for a circular tube works out to 2 over r naught. Here I should specify that r naught is the radius of the tube and d is the diameter of the tube. So the anyway, 2 over r naught squared times integral from 0 to r naught of u of r dr. Okay, so this is the mean velocity for a circular pipe. Okay, and the operating principle here is there's some amount of mass flowing through the pipe. If you were to make the velocity uniform, this is the velocity that would get the same amount of mass crossing, you know, a control surface through the pipe per unit time. Okay, we're also going to define a Reynolds number based on diameter as u sub m d over nu, okay, which can be defined as 4 m dot over pi d mu. Or if we wanted to plug it into right, our expression for um there, it would just be d over mu 2 over r naught squared 0 to r naught, right, u of r dr. Here's the Reynolds number. And then, right, when we were considering flow through pipes back in fluids, the thing that we were usually concerned with at the end of the day was how much power does it take to force some flow through a pipe, okay, which came down to what the pressure drop was. And we got to that through this thing we called the friction factor. So F defined as negative dp dx times d over rho squared over 2. And so from this pressure drop, right, if you know the friction factor, you can say, and you know the length of the pipe as well as its geometry and the mean flow rate, then you can figure out how much lower the pressure is going to be at the downstream end than the upstream end. And therefore you can figure out what kind of pressure jump, right, what kind of pressure boost a given pump needs to provide in order to drive the flow with those given conditions. And from that, you can figure out the pump power, right? This is relevant to heat transfer, right? Because this has a lot to do with things like flow through heat exchanger tubes. Comes down to, at the end, how big of a pump you need in a lot of cases. So you get friction factor from either the expression 64 over the Reynolds number. This is the case only if the Reynolds number is less than approximately 2300. Which corresponds to laminar flow. Back in fluids, we used 2100, but we're going to go ahead and stick with the book we're using now. If they want to say 2300, it'll keep things consistent. The difference between 2100 and 2300 is so small. I mean, it's not important. This is all very much finger in the wind kind of numbers. Okay. And then, and then we say that F is a function of the Reynolds number and the relative roughness of the pipe we're considering if the Reynolds number is greater than about 4,000, which corresponds to turbulent flow. And we get F in these cases from this thing we called, right, the Moody diagram, which was this big graphical set of curves that had right, Reynolds number on one axis, a bunch of different curves for different relative roughness ratios, and then on the y-axis had a friction factor. We're going to be breaking out the Moody diagram again later in this class, or in this chapter. But for now, I think that wraps up the considerations of the fluid flow, the hydrodynamic aspect of flow through a pipe. Got mean velocity, Reynolds number, which defines whether it's laminar or turbulent, and we've got the friction factor, which tells us how much oomph we need to provide to the flow in order to get it through a pipe with some dimensions and some velocity. Okay. Okay, so what about the thermal aspects of flow through a pipe? We're going to draw a figure that looks very similar. So when we just sketched, get me my pipe once again. X R. So the incoming flow in this case, right, we've seen this before as well. Let's say has is a distribution of temperatures it is uniform at the inflow. So we'd say this is T infinity, and right that the whole thing is flowing in at U infinity. So just like in the case of the velocity, right, we're going to end up with a boundary layer, but this one is going to be the thermal boundary layer, not the velocity boundary layer. So thermal BL, which means that the thickness of this thing is this delta T. And once again, at some point, these two boundary layers, or the entire boundary layer, is going to meet in the center of the pipe. And when that happens, we're going to get this change from, right, this regime of boundary layers abutting a region of constant temperature in the middle to okay. So once again, where before these boundary layers meet, we call this the thermal entrance region, and downstream of this point, we call this thermally fully developed flow. Let's go ahead and say that the surface here is at some temperature Ts, and once again, diameter R naught, or sorry, radius R naught and diameter D. So we'll go ahead and call this point where this fully developed flow occurs. In this case, we'll call this X, FD, comma, T for the fully developed X location for thermal flow. All right, one big difference between velocity and thermal boundary layers. This is a bit weird to think about, but it's important to remember, right? One big distinction here. For a velocity boundary layer, or for a velocity fully developed flow, I should say, we said that basically du dx is equal to 0, right? The flow is no longer evolving in the x direction. But for a thermally fully developed flow, that's not the case. The rate of change of temperature with x is not equal to 0, even downstream of this fully developed point. So that begs the question, why do we even justify calling it a fully developed flow? Right? It's clearly still changing. So what gives? Well, first off, why does this make sense? Right? If the temperature of the surface is warmer than the temperature of the fluid inside of it, okay, then we expect that no matter how far down the length of the pipe we go, the fluid's going to continue to heat up, right? As long as there's heat transfer occurring into the fluid. Or conversely, if we're pulling heat out of the fluid, okay, if we pack the this fluid in ice, or we cool it with Freon, then we expect that as fluid goes through it, or this pipe, sorry, if we pack this pipe with ice or run Freon across it, we expect that this fluid travels through the pipe, it's going to continually lose thermal energy and continue to cool down. The way we define a fully developed flow then is as such. A thermally fully is one in which the shape of the temperature distribution remains constant on X. And by shape, right, I mean if we were to take this temperature distribution and scale it as a non-dimensional variable, so if we write out the dimensionless temperature, say Ts minus T, Ts minus T mean. Okay, so we've got our local temperature, right? Temperature at a point, surface temperature, and mean temperature. We'll define this in just a second. Define it, yes. So theta is defined as this, which means that theta is scaled and non-dimensionalized, right? The fully developed flow is one such that d theta dx is equal to 0. So the idea here is that we're not concerned with this term being unchanging on x. We're concerned with this entire term not changing on x. So remember this is an important definition, and a less obvious conclusion that we could draw from this, we're not going to go into the derivation, is that h dh dx is equal to 0. So h is constant in the fully developed region. Okay, so I mentioned this thing here, this mean temperature, T sub m. Just like we defined a mean velocity, right? We require this mean temperature because inside of the pipe, in a fully developed flow, we no longer have a free stream, right? It's not there's no far away from the surface where we can define a reference temperature or reference velocity. So we have to come up with one that is consistent at any point in the pipe. So this mean temperature, we will figure out how to get using a similar principle to the one used to get the mean velocity. We might think, right? We might say, all right, the mean temperature, our initial naive approach might be that T sub m, would be 1 over A integral over area of temperature dA, right? That seems like a reasonable way to come up with a mean temperature. This is not it. Okay, I want you to put a big X through that. The idea here is we don't want just an algebraic mean of the temperature. What we're concerned with is finding a temperature that, if carried across a control surface by the mean velocity, okay, U sub m, will represent the same amount of thermal energy flowing across that control surface as the actual flow. Let me draw this schematically. Essentially, if we have our actual temperature distribution and we have our actual velocity distribution, it is, we want this to carry, right, this is going to represent some amount of, if we have a control surface, then there's going to be some amount of thermal energy crossing that control surface at an instant in time. Okay, it's going to be this temperature being carried across that control surface. And we'd represent that as integral over the area of that control surface, or that cross-sectional area, of rho Cp times T U dA. If we wanted to simplify that and represent it as a mean velocity and mean temperature, the idea is we would say, okay, here's our equivalent mean temperature, here is our equivalent mean velocity, and we want the same amount of thermal energy to flow across this control surface. Rho Cp times AC times UM times Tm. So we get the mean temperature, and by setting these two quantities across from one another and solving. So what that gives us is rho UM AC times Cp Tm equal AC rho U P T dA. If we're dealing with a circular pipe, once again, then this is going to work out to T sub m is equal to 2 over UM R naught squared, integral from 0 to R naught U of R times T of R dr. So if we want to find the mean temperature and we want to find the mean velocity, or well, if we want to find the mean temperature first, we have to find the mean velocity, okay, U sub m, and then we have to perform this, what turns into often kind of a messy integral, but we know how to do integrals, right? We've done enough calculus at this point. The integrals shouldn't scare us. We have to evaluate the integral of the product of the velocity and the temperature over the cross-sectional area of the pipe. Oh boy, we're running out of time. So last thing here is going to be an energy balance. Okay, so if we consider a flow, kind of like we drew up here, flow through a section of this pipe. X, R. Let's go ahead and draw this as red. So we're taking a slug, sort of a cylindrical control volume in this pipe, right? So anything that flows through this pipe has to flow in this side and out this side of this control volume. we'd say that we have m dot in flowing in and m dot out flowing out, right? Because it can fly and flow. Those are going to be the same quantity. And we say that the temperature up here is going to be Tm, and the temperature where it leaves this control volume is going to be Tm plus some small jump in the mean temperature. Okay, so writing out an energy balance from our first law, we'd say that E stored is equal to, right, E in minus E out dot plus generation term. We don't have any energy generation, and we're going to assume that we're dealing with a steady state flow. Okay. Our E in, okay, is going to be composed of two parts. M dot times the specific heat capacity of the fluid times the temperature entering the control volume, plus, and I haven't drawn this component yet, I'm going to assume that there is some convective heat transfer into the fluid, which we'll call dQ convective. The energy coming out of this control volume is just going to be m dot Cp times Tm plus delta Tm. Okay. So if we go ahead and plug E in and E out into our energy balance, we end up with 0 equal to m dot Cp times Tm minus Cp Tm plus delta Tm plus dQ convective, which, if we wanted to solve then for dQ convective, leads us with m dot Cp delta Tm. Okay. So the jump in temperature across this control volume, we're going to go ahead and apply a subtle version of a first order Taylor series and say that this is approximately equal to dTm dx times this distance delta x, right? So plugging that in, we end up with dq, oh, sorry, one more substitution to make here. We're going to assume that the small convective heat transfer in, okay, we're going to apply Newton's law of cooling to this and say that this is equal to, or not Newton's law yet, just we're going to say that this is equal to the convective heat flux times the perimeter of the pipe times dx. Okay, so the heat flux times the small surface area that heat flux is occurring through. And then finally, so plugging this all in, and we'll end on this last expression. Okay, this is going to lead to, if we plug this in and do some simplification, Q dot P is equal to m dot Cp Tm dx. This leaves us with the governing equation dTm dx is equal to Q convection times P over m dot times Cp, or if we plugged in Newton's law of cooling, P m dot Cp H Ts minus Tm. All right, So we're going to leave it off there. I'll leave this up on the board so you can finish copying down this expression. And we'll start talking about how to apply this as well as do a couple of examples first thing on Wednesday. Yes?
Q double prime P dx or D dx? You said it was the surface area, so...
P dx. Yes. P is the perimeter, so like if it's a... Yeah. I'll do a quick recap of this on Wednesday too.